The next thing we want to talk about is spherical mirrors. So if you haven't already, you might go back and play with the mirror simulation that we put on an earlier slide on Long Kappa as part of the classwork. It's not for points, but it is really useful to open that up and move around play around with the FET here. I think it's pretty useful to help you go forward. So the thing is, if the concept of an image is still unclear, it will be kind of difficult to get to what's coming next. Okay, so now we want to look at spherical mirrors. Remember, these mirrors are truly spherical. If you look at the left here, we have a piece of a spherical mirror and removed it from a sphere, and it's reflective. So it's kind of like if you had a Christmas ornament and then you just break a piece out of it. So it's not, the picture shows a curved line. It's not just a curved line, it's actually a part of a full sphere. So it's not just a bent mirror, it's a spherical mirror. Okay, so there are two kinds of spherical mirrors. There are concave mirrors, where the mirror is curved, where the top and bottom of the mirror bend towards from where the light is coming from. Usually people remember this because it is like the mirror makes a little cave. Convex mirrors are where the top and bottom of the mirror curves away from the source of light. Now we want to define the center of curvature. The center of curvature in a spherical mirror is the center of the sphere. Remember, the bent line that we show you is really a sphere, so the center of that sphere is described as C, and this is the center of curvature. This is also the radius of that sphere. This is true for both concave and convex mirrors, and for the concave mirror, the center of curvature will be on the same side of the mirror as the light, and in a convex mirror, the center of curvature is going to be on the opposite side from where the light is. Now, if we shine light from a distant source towards a concave mirror, this distant light, it will all be running parallel, and when it hits the concave mirror, it focuses all of the rays, and they cross at what we call the focal point. The focal point is where the distance EM rays all intersect. So if you have just a generalized bunch of light shining at it, the focus point is where all of that light is focused down. So notice that this happens to the left of the mirror, and we consider that side of the mirror, the left side on this case that has the light on it, to be positive. This effect is used in satellite dishes, for example, so radio waves travel a long distance, so the satellite dish reflects and focuses those rays onto the detector, so the signal is much stronger and all of the EM rays cross at that focal point. So you will want to put your detector at the focal point. For a convex mirror, the law of reflection disperses light that is traveling from a large distance, and if we track the rays backwards, they seem to come from a point behind the mirror that we call the focal point. Again, the focal point will be 1/2 the distance from the mirror to the radius of the sphere. This means that the light appears to be coming from behind the mirror, so it is a virtual point, so it's negative. So the focal point of a spherical convex mirror is -1/2 the radius of the spherical mirror. So if we have parallel rays of light, and it will reflect and cross at the focal point, or it will appear to come from a focal point from behind the mirror in the case of the convex mirror. Also, if we emit light at the focal point when it hits the mirror, it will produce a parallel set of light rays for a convex mirror or a concave mirror, while in a concave mirror, if the light is heading towards the focal point, it will then produce a parallel rays of light. At the center point, a ray of light that points at the mirror and can reflect straight back along the path where it came from. So, the idea is that if we want to track how the light rays bounce off of a mirror, we want to define 3 rays that tells us what will happen to the light rays that go through our mirror. In principle, we only need 2, but having a third gives us a sanity check to see that if it all makes sense. So we will look at a concave mirror here, and we want to define 3 special types of light rays. The first is the P-ray. The P-ray is the light that is traveling parallel to the center of the axis, and it will reflect and go through the focal point, so remember P is for parallel. The F-ray goes through the focal point, and it reflects to be parallel to the axis. The C-ray travels through the center of the radius and reflects back towards the center of the radius. The key is that we want to find these three rays as they travel through the point on the object that we are interested in. So let's look at an example of this. So we have an object that is inside of the focal point, so our red arrow here is our object, and we want to find our rays. So the P ray starts from the object, and it runs parallel to the center of axis, so it just runs straight to the right, and we start at our object and move towards the mirror, parallel to the axis. And then once the light hits the mirror, then it's going to reflect and go through the focal point. The focal ray, we start at the object, and the light travels on a line that goes through the focal point and the object and then hits the mirror. Once it hits the mirror, it becomes parallel, and so that confirms that that's the F ray. And the C ray travels through the center of the radius, so the C point, and then it travels through the object and then to the mirror. So notice that there the reflection is straight through the C point and back again, so it's really just sort of one ray. Now that we've drawn these three lines, we continue them through the mirror to see what the image is. Notice the lines don't cross anywhere, so we don't have an image. The image is where the lines cross. The lines cross at the object, but that's the object itself, so we already knew that that was a possible source of an image. But if we follow the lines through the mirror, they finally cross on the other side. So once again, we have a virtual image, so it's on the right side of the mirror where there is no light. Notice that the image is now taller than the actual object. So our image appears to be larger than the object itself, so it is magnified. Also, it appears to be a little bit further from the mirror than the object itself, so the distance to the image has changed as well. So for a concave mirror, there are three possibilities. The object is inside of the focal point, it is between the focal point and the center point, and it can be beyond the center point. So on the first slide, we did the case where the object is inside the focal point. If we put our object past the center point, as we show on the left here, so now we draw our P ray parallel from the object, and it then bounces off the mirror and through the focal point. We draw our F ray that goes through the focal point and then bounces off the mirror and goes parallel. And then we draw our C ray that goes through the C point. Here, all of our lines cross below the center axis, so our image is now upside down. Also, it is on the same side of the mirror as the object. There is light going through the image, so this is what is called a real image. Also, the size of the image is smaller than the original object, so now our magnification would be less than 1. Okay, I think I've shown enough now that you should just go ahead and practice drawing these rays, and hopefully I've shown that it's useful for understanding how an image forms. So now it's your turn. So remember, the rays go through the object. If it's parallel, then it's a P ray. If it goes through the focal point, then it's an F ray. And if it goes through the center point, then it's a C ray. Good luck.